welcome to the HL component of spectroscopy. In the SL topic, we discussed a number of key analytical techniques used to identify the structure of an organic compound, and the structural identification of compounds usually involves a combination of different techniques, in particular infrared, proton NMR, and mass spectroscopy. So by the end of the unit, you should be able to identify compounds using these techniques, introduce the concept of high resolution proton NMR and what that actually means, and also know about the structural technique of X-ray crystallography. Also by the end of the unit, you should be able to explain why we use TMS as a reference standard, and also to just deduce the structure of a compound given information from the analytical techniques that we have covered. So in terms of resolution, we've only looked at low resolution NMR at the moment, but for HL we look at high resolution NMR. Okay, so spin coupling we already discussed creates slightly different energy levels, creating splits in peaks. Okay, we've only seen the low resolutions peaks, which are massive in terms of the protons and different carbons, but you can also have the protons on the same carbon being split. You don't see that in normal low resolution. You need to use high resolution proton NMR. So the first thing we have to do is get a decent standard to work out what the zero chemical shift is. Okay, and the one we've chosen is tetramethylsilane. And the reason why we do this is three reasons. The first one is all the hydrogens are equivalent. Okay, so you only get one reference line in both high-res and low-res spectroscopy with protons at 0 ppm. Also, silicon has a lower electronegativity when compared to carbon, so the silicon-hydrogen bonds or the resonances associated with them do not overlap with the carbon-hydrogen ones. Also, it's chemically inert. It's soluble in most of the reaction solvents that you would use, and can also be very quickly removed by boiling, usually under reduced atmospheres. So what is high resolution proton NMR? Well, in the example ethanol, okay, so what we've got here is we have the red dotted lines illustrate what you would see in low resolution proton NMR, and the black lines illustrate what you see in the high resolution NMR. Okay, so what happens is that the high resolution proton NMR spectrum can show further splitting at some absorptions. And these splitting patterns result from spin-spin coupling. And to understand spin-spin coupling, we'll continue on to the next slide. So in high resolution proton NMR, the protons on the same atom do not split as they behave as a group. Okay, so you just see that as one signal. However, protons on non-adjacent atoms do not interact with each other. So what do we mean by that? So if you have a 3 rings, okay, and we have a proton here and a proton here, they don't interact. However, if you have a proton here, these two will interact. Okay, that's what we're saying. And protons on hydroxyl groups generally do not split. Okay, so this is an example of a low-res proton NMR spectra, okay, just singlets, and this is the high-res spectra of the same compound. And you can see now there's going to be interaction between hydrogens on adjacent carbons. Hence, the hydrogen on the aldehyde functionality is seen as a quartet, and the hydrogen on the methyl group, or the methyl group hydrogens, are seen as doublets. And we're now going to look into more detail as to why that occurs. So now we're going to look at in a little bit more detail at the high resolution NMR or proton NMR of ethanol and why you get the signals you do. So we're going to break it down. First, we're going to look at the effect of the proton on the aldehyde group on the spins of the adjacent methyl group. So protons have a nuclear spin. They hence have their own magnetic field, which is associated with them. So every proton can act as a little magnet. So the spin can either be clockwise or anti-clockwise, and we're going to look at those two examples. So in the first example, the magnetic field produced by the spinning proton on the aldehyde group is clockwise. This increases the local magnetic field strength experienced by the protons on the methyl group, because it aligns with the external magnetic field produced by the electromagnet. Okay, so delta E gets larger. Okay, and this is known as de-shielding. And what happens to the chemical shift is it moves known as downfield. It gets larger. Okay, gets larger. The other possibility is the magnetic field is of the proton on the aldehyde group is now anticlockwise. This decreases the local magnetic field experienced by the protons on the adjacent methyl group. So delta E, the change in difference in energy of the non-aligned neighboring proton, is now reduced. Okay, this is known as shielding, and this pushes the signal in parts per million, the chemical shift, upfield. And this is why you see this splitting. So in low resolution, you just see one signal, and then in the high resolution, you end up with two signals, 1 and 2. One is the de-shielded protons, and one is when the protons are shielded, depending on the spin of the adjacent proton on the aldehyde group. So what about the effect of the protons on the methyl group on the spin of the proton on the aldehyde group? Well, again, you have the external magnetic field. All the protons on the methyl group are aligned with the external magnetic field, then what you're going to have is you're going to have this signal here. Okay, it's going to be moving downfield. I should just move over there, move it downfield, and it will show as just that small singlet there. And these signals here, this first one here, is going to be also slightly downfield, but this will correspond to, it's going to be 3 times the intensity, because you have 3 ways that you can rearrange 2 protons with and 1 against the external magnetic field. Okay, and then correspondingly, you have the other example where you have 1 proton with and 2 against the external magnetic field. Okay, and there you have shielding in that particular case, more shielding than de-shielding. And finally, you have where they're all against the external field, and those protons are completely shielded. Okay, and that's why you have the ratio of 1 to 3 to 3 to 1 in the signal. Okay, because these guys are completely shielded. In that particular case, or that one particular proton, sorry, is shielded, and in this particular case, that one particular proton is now completely de-shielded. And the 2 in the middle are combinations of that. So another example is the splitting of 1,1,2-trichloroethane. So you get 2 combinations, the HA1 and the HA2, and also HAB. Now, because these guys are equivalent hydrogens, they do not split each other's signals, so you don't see splitting between them. Okay. So the interfering magnetic field is called shielding. Occurs when nearby hydrogens on the next carbon are split by the HB and vice versa. So in terms of the effect of spin coupling, okay, HB can have 2 alignments with respect to the applied magnetic field. Either it's going to be with it or against it. Okay, so when HA1 and HA2 spin with the magnetic field, HB gets de-shielded, okay, and as we've discussed, it moves downfield. Okay. And then you've also got HA1 and H2 having mixed spins, okay, so one is with the field, one is against, then you're going to have the HB peak in the middle. It's going to be a combination. And that's going to be basically in terms of intensity 1 to 1 to 1, because there's 2 possible combinations. Yeah. And then for HA1 and HA2 spin against the magnetic field, then HB is going to be shielded, and it's going to be moving, okay, upfield, because now what you've got is you've got a lower effective magnetic field being experienced by HB now. Okay, so it's now moving upfield. So what you do see then is you see essentially a doublet for HA and a triplet for HB, because remember HA is going to be equivalent to each other. And the reason you see this is because HB can only exist either as a spin against or spin with the magnetic field. Okay, so it can either oppose it or it's going to be aligned with it. So there's only two possible ways that particular proton can interact with the magnetic field. That's why you only see a doublet and nothing more. Because in the case of the HA interacting with HB, the shielding effect of one cancels the de-shielding effect of the other. Okay, so hence the net effect is that there is no change in chemical shift of the single peak seen on the original low resolution proton NMR. And the number of splits, therefore, if you maybe you've already worked it out, is going to be based on the idea of Pascal's triangle in terms of intensity. Okay, now this is an important point, okay, when it comes to structural elucidation, that the number of splits in a peak for a particular hydrogen is determined by counting the number of neighboring hydrogens on the adjacent carbon, and then by adding 1. So I'm going to also put that there on adjacent carbons, not just every carbon. Okay, so for example, if you have CH2, CH3 as a group, and say that's going to be right next to a carbonyl, then that guy, these protons here, they have 3 adjacent protons. Okay, so what you're going to see is something like that, known as a quartet. Okay, known as a quartet for these guys, and the protons on there are only going to have 2 adjacent protons next to it, so it's going to be n plus 1. So it's going to be seen as a triplet of 1, 2, 1 intensity. Okay, so it's going to be something like that. That's what you would observe, and it's known as a triplet for these protons here. That's an important point when we're looking to elucidate the structure of particular compounds. So let's look at the example of butane 2-one to illustrate this point. Okay, so let's just do the structure of butane 2-one. Okay, and let's just kind of predict what the NMR spectra will actually look like. Okay, so we've got CH3, C double bond O, CH2, and then also CH3. So what you can do is basically break down the areas of hydrogens on the carbons into areas. Okay, so or letters. So you've got A, area B, and area C. Right. So let's first work out what kind of signals you'll generate. Okay, so remember it's going to be like n plus 1. Okay, so n is the number of protons on the adjacent carbon. So A, you will see it's got its adjacent carbon has how many protons? None. Okay, so n plus 1, you will just see 1 signal, and that will be a singlet. Okay, we'll put S as singlet. And then we've got B. Okay, so this one has this one here has again 0. This one would be 3 signals. So this would be n plus 1. So you'd see that as 4 signals. Okay, and that would be known as a quartet. Okay, and then C, it's got only those hydrogens there next to it, so it would be 3, and that would be seen as a triplet. Okay, using Pascal's triangle, you can work out the relative intensities. Okay, so if you look at your data booklet, okay, the CH3, it's predicted is, well, we don't really know, it's next to a carbonyl. Okay, so a carbonyl probably would put it at around 2 ppm, okay, because a normal methyl group will be about 1, but the carbonyl will de-shield it, so it'll be about 2 ppm. Okay, the quartet, if you look at the data booklet, is predicted around 2.2 to 2.7, okay, because again it's right next to a carbonyl, so that will be that CH2 will be about 2.2 to 2.7 ppm, and then the one next door, the methyl group, right next to another alkyl group, would be, according to our data booklet, be around about 1 ppm. Okay, so what you would actually end up seeing would be, if this is the stretch, and we've got to about 11 here, and this is going to be 0 with our TMS, okay, then at 1 you would see a triplet, okay, so it's about 1 there, you'd see a triplet, that's very poor drawing, but so, and then at, there's 2 there and 3 there, so at 2 you would see a wonderful singlet, okay, it's one singlet, and then at 3 you'd see nothing going up into, or at 3 you would see a quartet around about 2.7, okay, so that would be, using Pascal's like that, okay, so you see a quartet, so you see a singlet there, a triplet there, and a quartet there, and so on and so forth. So that would be the signals that you generate for that particular structure. Okay, and that's how you'd use it using a combination of your data booklet. So as you can see, butane 2-none consists of hydrogen present in 3 different chemical environments, and the integration traces therefore would have a ratio of this one at A would be 3, okay. That one at B would be 2, which is your quartet, so that would show as 2, and then the triplet would show as C, which is also 3 if you integrated it. Okay, so that way you could work out predict what the spectra would look like. So another important aspect is high resolution NMR is integration. Okay, so integration is the area under the graph and gives you the relative number of hydrogens in a molecule. This also determines to help you assist in determining the molecular structure. Okay, that's quite useful. And also in your data booklet you will have associated values for all these signals, so you can kind of work out where these signals are coming from. So here's an example of a problem that you might be given. Okay, so a feature of some proton NMR spectra is the electron withdrawing effect of electronegative atoms. Okay, these atoms can cause protons to produce peaks of high chemical shift value, often between the range of 2.5 to 4.5 parts per million. Consider the proton NMR spectrum of an unknown compound D with a molecular formula C4HO2, and it is known to have an absorption in the IR spectrum corresponding to carbonyl absorption. Use this information to determine the structure of D. So pause the video now and let's see if you can work that out. Okay, so what you should have seen is D could be two possibilities. Okay, a combination of two different esters, because there is a 3 peaks with a 3 to 2 to 3 ratio. This explains the splitting of a singlet, a triplet, and a quartet. And methyl propanoate is a correct isomer because of the higher chemical shift value of the singlet. Okay, 3.6 as opposed to 2 to 2.5. So you should have got methyl propanoate as your answer.
Let's say we're given this molecular formula, C5H10O, and this proton NMR spectrum, and we're asked to determine the structure of the molecule. The first thing you could do is calculate the hydrogen deficiency index. And so if we have 5 carbons here, the maximum number of hydrogens we could have is 2n plus 2, where n is equal to 5. So 2 times 5 plus 2 is equal to 12. So 12 is the maximum number of hydrogens. Here we have only 10 hydrogens, so we're missing 2 hydrogens. We're missing 1 pair of hydrogens, and so therefore the hydrogen deficiency index is equal to 1. Immediately, that makes me think about a double bond might be present in this molecule, or 1 ring. Let's go down to the integration values. So for this signal, there's an integration value of 27. For this signal, the integration value is 40.2. For this signal, it's 28.4, and for this signal, it's 42.2. Remember what you do. You divide all 4 integration values by the lowest one. So the lowest one is, of course, 27. So 27 divided by 27 is, of course, 1. 40.2 divided by 27 is pretty close to 1.5. 28.4 divided by 27, that's pretty close to 1, and 42.2 divided by 27 is once again pretty close to 1.5. Remember, these are just the relative numbers of protons giving you these signals, but you can't have 1.5 protons giving you a signal. We need a whole number, and we need to account for 10 total protons here. So if we multiply 1 by 2, then we get 2 protons. So this signal represents 2 protons. If we multiply 1.5 by 2, we get 3. So this signal represents 3 protons. If we multiply 1 by 2, we get 2, and if we multiply 1.5 by 2, we get 3. So if you add all those up, 2 plus 3 plus 2 plus 3, that's of course 10 protons. So now we've accounted for all 10 protons using our integration values. Next, let's look at each signal one by one. So we'll start with this signal. So we have a CH2, since we have 2 protons. So this signal represents a CH2. How many neighboring protons do those CH2 protons have? Right, so we can figure that out by the number of peaks on the signal. So this signal here has 1, 2, 3 peaks. And if you think about the n plus 1 rule, if you have n neighbors, you get n plus 1 peaks. So if we have 3 peaks, all we have to do is subtract 1 to find out how many neighboring protons. So 3 minus 1 is equal to 2. So this CH2, these CH2 protons have 2 neighboring protons. Let's think about the chemical shift for this signal. So the chemical shift for this signal is between 2 parts per million and 2.5. And that's in the region for a proton next to a carbonyl. And that would make a lot of sense because we calculated an HDI of 1, indicating there might be a double bond present, and we need to account for an oxygen in our molecular formula. So let's go ahead and draw in a carbonyl, and these CH2 protons are next to the carbonyl. We know that because of the shift, right? The carbonyl, the oxygen de-shields these 2 protons a little bit and gives us a higher value for the chemical shift compared to something in an alkane type region. All right, let's color these protons in here magenta. So we're saying this signal is due to those 2 protons. Let's move on to the next signal. So we have 3 protons, so that would be a methyl group, so CH3. How many neighboring protons for those methyl protons? Well, there's only 1 peak here, so 1 minus 1 is 0, so 0 neighboring protons. What about the chemical shift? So the chemical shift for this signal is once again past 2 parts per million. So this signal is de-shielded, right? So these protons must be de-shielded a little bit, and those must be next to our carbonyl. So we'll draw in our methyl protons, right, being de-shielded because they're next to the carbonyl. And let's make these blue. So these protons in blue here, these 3 protons are giving us this signal. And we should expect 0 neighboring protons. Right? So those protons are on this carbon, and the next door carbon has no protons on it. So 0 neighboring protons makes sense. Move on to the next signal. So this signal represents 2 protons, so that's a CH2. How many neighboring protons? Right? Well, let's count up how many peaks we have. 1, 2, 3, 4, 5, 6. So 6 peaks. So we subtract 1 from that. So 6 minus 1 is 5. So we would expect 5 neighboring protons. Let's move on to the next signal. 3 protons, right? So that's a methyl group, so CH3. How many neighbors? Well, we have 1, 2, 3 peaks. So 3 minus 1 is 2. So we would expect 2 neighboring protons. Now these 2 signals, right, this signal here and this signal here, we're talking about under 2 parts per million now. So these must be the furthest away from the carbonyl, right? So they're not being de-shielded as much as the 2 signals in this direction. So these 2 neighboring protons for the methyl group must be these 2 protons right here. So let's go ahead and draw that in. So we have our methyl protons right here. And let me make these protons red. So these protons right here in red are giving us this signal. And from the signal, we know that these methyl protons are next to 2 neighbors. And so we must have a CH2. We must have a CH2 next to that methyl. And so let's go ahead and draw in our CH2. And this CH2 must be this signal right here. All right, so let's think about how many neighbors. We expected 5 neighbors for these CH2 protons. Let's count them up. 1, 2, 3, 4, 5. So 5 neighboring protons matches what we see on the NMR spectrum. Now, those protons, those magenta and red protons, are actually in different environments. And so the simplified version of the n+1 rule isn't quite true, but it works for this example. So we're going to go with it because all we care about is getting the structure of our molecule here. All right, so let's think about the red protons again, right? So the red protons are supposed to have 2 neighbors. So how many neighbors do the red protons have? Here's 1 and here's 2. So this makes sense. So that one makes sense. This one makes sense right here. We just talked about that. Let's think about the magenta protons. So the magenta protons were supposed to have 2 neighbors. So let's look at the carbon next door to this one. So here's the carbon next door. Here we have a neighbor, and here we have a neighbor. So this makes sense. And then we already talked about the blue protons, right, having 0 neighbors. So everything seems to make sense here. And to sum everything up, make sure to count all of your atoms, and you will get, of course, 5 carbons, 10 hydrogens, and 1 oxygen when you do that. So this is the dot structure that we were trying to find. Let's take a look at another one here. So we have a molecular formula of C8H10, and let's go ahead and calculate the hydrogen deficiency index. So if we have 8 carbons, then we can have a maximum of 2 times 8 plus 2 hydrogens. So 2 times 8 is 16 plus 2 is 18. So for 8 carbons, 18 hydrogens is the max. Here we have 10 hydrogens. So we're missing 8 hydrogens, or we're missing 4 pairs of hydrogens. So the hydrogen deficiency index is equal to 4. Remember, anytime your HDI is equal to 4, you should think about a benzene ring. So I'm going to go ahead and draw a benzene ring in here. And let's look at the integration. All right, so sometimes you'll see the integration given like this. So this represents 5 protons for this very complex looking signal right here. This signal over here represents 2 protons, and this signal represents 3 protons. So let's go back to these 5 protons with this complex signal, right? This is in the aromatic range, right? So approximately 6.5 to 8. Those must be 5 aromatic protons. So we can go ahead and draw in 5 protons off of our benzene ring. So even though those protons are in slightly different environments, right? Because this integration value is 5 here, and we know a benzene ring is present, we're done, right? We don't have to worry about the slightly different environments. We know that these 5 protons are giving us this complicated signal over here. All right, next, let's look at this signal. So 2 protons, so that must be a CH2. How many neighboring protons for the CH2? Well, there's 1, 2, 3, 4 peaks. So if there's 4 peaks, 4 minus 1 is 3. So these CH2 protons have 3 neighbors. All right, let's look at this next signal. So 3 protons. So this must be a CH3. How many neighboring protons do we have for the CH3 protons? Well, we have 1, 2, 3 peaks. So 3 peaks, 3 minus 1 is 2. So 2 neighbors. And so 2 neighboring protons, that must be these 2 neighboring protons. And so we can go ahead and draw an ethyl group, right? So this is an ethyl group pattern over here. So there's a CH2 and there's your CH3. So let's draw in all of our protons. So we have these protons and we have these protons. And let's color coordinate here just to make sure everything makes sense. So these red protons right here, they must be giving us this signal, so these methyl protons, right? We'd expect 2 neighbors because we have 3 peaks on our signal. And here are the 2 neighbors, 1, 2, so 2 neighboring protons. Let's look at these 2 protons next. So these 2 protons are giving us this signal. We would expect 3 neighbors because we had 4 peaks, 1, 2, 3, 4. So 3 neighbors, so here's a next door carbon, so 1, 2, 3 protons, and then this is also a next door carbon, but there are no protons on this carbon. And so we see only these 3 neighbors, and so everything seems to make sense. And once again, count up all of your atoms and make sure you've accounted for everything. For example, right, you have 8 carbons you have to worry about. So on your ring we know there are 6. 1, 2, 3, 4, 5, 6. And then we get 7, and then we get 8. So the 8 carbons is correct. And then if you count all those up, we have our 10 hydrogens accounted for too. So this is the NMR spectrum for ethyl benzene, right? And this one was a little bit easier than the previous example.
So finally, let's look at X-ray crystallography. So X-ray crystallography essentially is a structural technique that can be used to identify the bond lengths and bond angles of crystalline compounds. And here we have the structure of DNA, which was discovered by Rosalind Franklin in 1953. So the chemical community as a whole often shares chemical structure information around crystallography. And examples can include the Royal Society of Chemistry and the Worldwide Protein Data Bank. And it illustrates the international dimension of global scientific research and the global scientific community.